So, good afternoon, students. Again, can you hear me and see my screen?
Yes, Prof.
Thank you. Yeah, so maybe I'll just wait for another 1 minute or so before I start the lesson. Okay, so I think let's start. Yeah, so we are only left with line integrals, which is actually the integration of a vector field along some line. So therefore, the vector field will be given, the line will be given. So therefore, you just have to really perform the integration. Okay, but of course, it's not like a kind of direct integration in the sense of those presented in the last topic, topic 7, because these are vector functions, right? So actually, there are two types of line integrals, and I'm only going to focus on the vector line integral represented by the right diagram here. Now, on the left, there is this corresponding line integral, which is called the scalar line integral. Okay, so scalar line integral, right? Because your next trimester, your electromagnetism doesn't focus too much on line integrals, I mean on scalar line integrals, because effectively magnetic fields and electric fields, they are vector fields. Okay, so electric field and a magnetic field, right? They have magnetic field lines, for example, a magnet, right? You know that the magnetic field lines are emanating from a north pole. Then after that, kind of like going around a bar magnet and then goes to the, I mean, converging towards the south pole. Okay, so actually you can draw the arrows, right, representing the magnetic field lines of a bar magnet, for example. So therefore, we have the magnetic field being a vector field. Similarly, for an electric field is also a vector field. Okay, so therefore, with respect to that, the vector line integral will be more relevant. So I'm going to be focusing on the vector line integral, which means the scalar line integral will not be tested. Okay, scalar line integral will not be tested. And of course, later on, the scalar line integral slides, as well as the examples, I will be skipping. Okay, so I will just put in the material in the writings uploaded, and then you can go through yourself, right? But let me just quickly mention that what is actually a scalar line integral. Actually, a scalar line integral is really just an integral of a function along some line or along some path. So more generally, right, the line may not be a straight line. Okay, the line can be actually a curve. So therefore, we say that the scalar line integral in this case, right, is the integral of some function f. For example, if the function f is a f of xy, which is represented by this orange surface, then you can see that, right, if you are integrating f along the curve C. So this C here represents the curve that is on the xy plane. Okay, so this C is this C, right? Integration along curve C. This is how they denote a line integral. And this ds, right, is actually you take f, right, and then you multiply by the width ds. So where is ds? Actually, ds is just a small section of curve C. So if I may, right, I can draw. Okay, so what is ds? So ds is actually this distance. This is ds. Okay, so ds very similar to like dx. If you integrate, because when you do a scalar line integral, for example, you have integration of f of x dx. So this is also a scalar line integral. So this is a scalar line integral only along the x direction. Okay, so which means actually your line or your curve C, in this case, it's not a curve, right? It's just a straight line, in the x direction. Okay, so therefore, when we are doing simple integration, right, of a single variable function in, let's say, topic 4, if I didn't remember wrongly, that's when you are introduced to integration. We are actually doing a scalar line integral, okay? But this line is actually only in one direction, right? In the x direction, for example, okay? So therefore, the scalar line integral more generally, right? This line or curve C can be any path in 2D space if your function is f of xy. Then can you do f of xyz or not? Yes, yes. You can integrate f of xyz along a path that is in 3D space. Okay, so the path can be like curving in 3D space. Can So basically, if you look at this diagram, actually it tells you what is the scalar line integral. The scalar line integral, right, is actually just the area of this blue surface. Because you take height f of xy times ds. So that means you are actually looking at this area. So this blue shaded area is f of xy because the height is f of xy. Then you take this height times width ds. So therefore, it's this shaded area lor. Correct or not? So this shaded area is like what? It's like dA. It's like dA. Okay, so you can see the same kind of stuff that is taught in topic 7, right? Being applied here again because it's the same idea. Okay, so therefore, this is actually your dA, the small, infinitesimally small areas. So then if you integrate along path C, what does that mean? That means you are summing up all these strips of area, right, over along the path C. Can Okay, so therefore you get a total area lah. So therefore this is the total area of this surface. Okay, the total area of this surface. Can So this is a scalar line integral. Okay, so I believe it's not too difficult to understand because it just extends from our single variable integration. Okay, but of course there are some technicalities or details, right, within this scalar line integral, right? So therefore I'm not going to focus on this. Okay, just to introduce you, and then later on the examples you can go through yourself. Okay, but not tested. More importantly now, right, I want to talk about the vector line integral. Okay, so the vector line integral is exactly what it says. It's an integration of a vector field or vector function, right? So we have seen this vector function in the earlier class already. So we are integrating the vector function along some curve C or along some line, okay, or along some path, regardless, right, of what it's called. So this is called a vector path integral or vector line integral. Okay, so once again, right, the path can actually be a curve. Okay, can actually be a curve. So now you see, so what's the thing about this vector line integral is that, right, now you have to integrate a vector function. Okay, then you ask yourself, how do you integrate the vector function? Do you integrate, like, for example, each component of the vector separately? The answer is no. Okay, the answer is no. So the vector line integral is defined such that, right, you have to integrate the dot product between the vector and the path direction. Okay, that means as you go along the path, right, at every point on the path there's a different direction, right? So along the path you take this small displacement. So that small displacement is actually given by dr. Okay, so you are displacing or you are moving along the path. Then every time you take a small displacement, you have a dr direction because you have a direction along the path at any point on the path. You take the dot product between that displacement vector and the given vector field f. Then you sum up these dot products. So therefore, you are like summing up all the dot products between f and dr. Okay, so interestingly, this is going to be the general formula for work done. Okay, because why? Force times displacement. This is like a force field F, for example. dr is what? dr is the displacement vector. This dr, later on I will talk more about dr. dr, right, is a displacement vector. Okay? So that means you look at this path, where's the displacement vector dr? So like if you're at this point, you can say that the displacement vector dr, right, is this. Okay, then if you're at this point, the displacement dr is this. Okay, then if you're at this point, the displacement dr can be this. So it's a very small displacement. In fact, it's infinitesimally small along the path. Okay, so dr is a bunch of small displacement along the path. Okay, so certainly you can see what this one same concept, force times distance move, or force times displacement. Then you sum up all the force times displacement. What are you going to get? Total work done. Okay? Because over very small displacement dr, right? You take the force multiplied by that small displacement, you are looking at what? At a small work done, infinitesimal work done over that small path. Understand? So you sum up all the work done along every section of the path. So therefore you get total work done. Understand? Okay? So of course this is the conceptual understanding, right? How you can actually integrate a vector field over some path to get the total work done. And this is important because, for example, in the magnetic field, you have a object that is subjected to the forces from the magnetic field. So therefore, if that object is moving along the magnetic field, then the magnetic field is going to have work done on the object. Okay? So then, of course, the work done actually relates to the energy consumption, for example, of your device, of your system. Okay? So we need to know the energy consumption so that we can maybe calculate the output or the mechanical efficiency, etc., of the system. Okay? So therefore, electromagnetic devices have this line integral that will give us the work done on energy consumption. Okay? So this is the application. So now let's look at how we characterize a path. Okay, so actually this relates to the usage of vectors, and this is a very beautiful, if you ask me, right, it's a very beautiful usage of vectors. Okay, now you see, a curve or a path, generally, of course, you can represent it using like a y as a function of x, right? Correct or not? So you can write it as y as a function of x, you can write it as x as a function of y, or you can write it as function of xy equals to constant. Okay, an implicit form lah, right? But it all represents some curve in 2D, for example. Okay, that's one way. All right, that's what we call maybe you can say the Cartesian way lah, the Cartesian way of representing a curve in 2 dimensions. You can also represent the same path using what we call parameterization. Okay, so the parameterization, I mean, sounds complicated lah, parameterization, but actually it is exactly what it means. Introduce a parameter, right? Introduce a parameter such that the x and y coordinate is a function of the parameter t. This parameter can be t, can be anything, doesn't matter one. Okay, so it's useful or intuitive to treat t as some time. Okay, as time lah, right? So you see, idea very, very, very elegant. Now, I say that, right, this path is described by this parameterized vector function r of t. So you see the r of t. Okay, so what happens is that, right, r of t will always point to the path. Okay, it's always pointing to the curve lah, to the curve C or the path C. Now, what happens is that this x of t, right, is the x component of the vector. So therefore, if I underline this x of t, right, where do you think x of t is? X of t must be this. This must be x of t. Okay? Then needless to say, you of course know where is y of t lah, by now. Y of t, right, will be the y component. So this will be y of t. Okay? So then obviously x of t, y of t in the respective component will be r of t. So this is very clear. Okay? So now what is the deal with the of t? Of t. So that means if you treat t as some time parameter, right? Need not be time, can be anything, doesn't matter. Okay? That is right. As time progresses, you are moving along the path. Okay? So as t progresses, you're just moving along the path C, right? So it's, for example, at this point, at the starting point, let's say you move from this point to the final point here, right? So at this point, maybe t equals to 0. Okay? Then maybe at this point, t equals to 1. Then maybe at this point, t equals to 2. Okay? So you see where I'm going. Maybe at this point, t equals to 3. Okay, so from the start point to the end point, maybe say 3 seconds or 3 units of time taken. Can you see that? Okay, so basically, this r of t can change one, right? At t equals to 0, where must be the r of t pointing? the so-called R of 0 lah. R of 0 must be pointing towards this point what? Correct not? Must be pointing towards this point at t equals to 0. So therefore, this arrow is actually R, the vector R of 0. Because t equals to 0 ma. Understand? Okay. Then, of course, generally it's called out of t. Then what about, let's say this t equals to 3, t equals to 3 point. So this t equals to 3 point, right? This one must be R of 3 lah. Right not? You sub in t equals to 3, then you get your vector law. The vector must point towards at this point law where so-called an object or particle or whatever, right, has reached that point already at t equals to 3 seconds, for example. Okay, so therefore this is what? This is actually just writing down the x and y in terms of a vector. So it's a very beautiful way of representing a curve in any dimension. Okay, in 2 dimension, 3 dimension, doesn't matter. So if it's in 3 dimension, then you got x, y, z lah. Can see Okay, so therefore let's stick to the plane, right, whereby we have only x and y coordinates. Okay, and x and y coordinates change accordingly. Okay, so change accordingly with respect to time t, for example. Right? Yeah. So therefore, this is called the parametric curve or parametric path, doesn't matter what it's called. Okay, so you can see that if I have a curve that is y equals to x squared, what is the so-called parametric representation or parametric equation? Okay, very simple what? Y equals to x squared. So I can just let x be t, for example. In fact, I can let x be anything. Okay, that means really, if you have a velocity function, of course, you can consider that velocity function. For example, how fast the object, right, is moving along the curve. Okay, then you have a velocity function for the object. Then, of course, you take the cosine and sine, you can get the x of t, y of t respectively, right? But however, in this parameterization is mainly mathematical. Okay, it's mainly mathematical, meaning to say we are just trying to introduce some mathematical tricks so that we can perform this line integral easily. Okay, so we don't care about the velocity function, right? There's no such thing as a velocity function in this respect, but we just parameterize it, right, by, for example, letting x be t. Okay, so just let x be t. That means I let x of t be t lah, right? If x is equal to t, but the path is y equals to x squared, what? Correct or not? So if the path is y equals to x squared and you let x be t, so if you let x equals to t, then quite obviously, y equals to x squared must be y equals to t squared. Okay, that means y equals to t squared, right, must represent this path, this curve lah. Okay, so therefore you can see t squared. So this one, how come you got t here? You just let x equals to t. Okay, so this is called parameterization. You see that? So you can see that, right? The vector function now becomes a function of t already because the components, x and y components, both contain some function of t. Okay, then of course you have the logical question. Hey, can you, is it possible that you don't let x be t or not? Can. You can let x be t square also can. But actually there's a meaning. When you let x be t, that means you're treating like x is increasing linearly with t. As t increases, right, the x will increase linearly also. But if you let x be t square, that means as t increases, x is going to increase quadratically. Okay, but actually it doesn't matter, right? It doesn't matter. That means in the integration, right, it will all work out to be correct. Okay, so you can let, right, maybe I write that all lah. Give you another parameterization or you can let x be, for example, t squared. So if let x is t, if x be t squared, right, that means y must be t to the power of 4. Okay, so if y is t to the power of 4, then your r of t will be t squared t to the power of 4. Is that right? So this is perfectly fine as well. Perfectly fine. Okay, but you during parameterization, typically we will just try to use the simpler functions. Okay, we use appropriate but simpler functions, as simple as we can. Okay, so there's no like good reason to introduce a square, right? Then don't introduce the square. Okay, to the parameterization. So you can of course let y be t also. If you let y be t, then x got to be root t, for example. Okay? Okay, so scalar line integral not tested, so I'm not going to go through this part. You can self go through. Obviously, the writings will include the details. Yeah, so let's look at this vector line integral in more detail. Okay, so just now I've showed you like the r of t here can parameterize already. Okay, so it's called parameterization. Just introduce a parameter so that your x and y, right, become some functions of t. Okay, so now after parameterization, what will be your line integral? Okay, now remember, okay, let's go back to the original definition of the line integral. It's integrating f dot dr. F is the given vector field. Okay, so now you have to find out what is dr, right? Correct not? Because f is given, then that means you have to include find out what's the unknown dr, the displacement vector dr. Okay, then just now I mentioned already what? dr is just a small displacement along the path C, okay, along some path given, right, where you're supposed to evaluate the line integral for. Now, this dr is an infinitesimally small displacement, okay, very small displacement. By now, you should know, every time you see d, that means infinitesimally small, not zero, but approaching zero, okay, very small. So what is this dr? Now, if you have parameterized your curve or path C using r of t, right? Right, a vector function. Okay, let's say you are moving from this point in this direction to the final point here. So your r of t, let's say at some t is pointing to this point. Okay, this point. Then after some time later, dt later, right? It moves to the next point at the end, or rather at the head of the arrow. Okay, so we move from tail of the arrow to the head of the arrow of dr. Okay, so move a little bit already lah. So therefore, what's the displacement then? The displacement must be dr Correct not? Must be dr But then your dr small displacement, right, can be velocity times time, what? So isn't this small displacement is equivalent to velocity times time. Okay, so the object moved from r of t to r of t plus dt. So it takes what? It has taken dt. Okay, the time taken, right? dt. So you take the velocity times time taken, isn't this displacement? So it's the small displacement dr, right? Fair enough. So now you see, this dr is exactly this r prime t dt. Okay, so we replace dr, right, by r prime t dt. So this is your dr vector. So we just replace by r prime t dt. Then makes everything so easy. You see, f, the vector field in red, okay, so I just draw a few arrows along the path. In fact, the vector field is everywhere. Every point xy, you see some arrow. You see an arrow. Okay, I give you a point xy, you can always calculate the x and y components. So therefore, you can draw the arrow as demonstrated in the earlier class. Okay, wait, let me underline. So this will be your vector f. Okay, but then because your r of t, now remember, r of t is always pointing to the path. Okay, and you are interested in taking the dot product, right? So which means you want those arrows that is on the path to dot product with the displacement vector. For example, you look at this point, right? At this particular xy, that means at this particular r of t, you're going to sub in the x of t, y of t into f. So you can calculate f already. Okay? Then after that, you take f, right, dot product with this dr, which has been evaluated to be r prime t dt. Okay? So you can see the thing here. But because your f, right, got two components, for example, in this case, is f of xy, so therefore, you got f1 component, which is the x component, and f2, right, which is the y component. Okay, so that means you just substitute that vector r of t into f1 and f2, basically the x of t, y of t, then evaluate this, and then dot. Now, this r prime is just x prime, y prime. So this one really, really straightforward, because since r of t is x of t, y of t, So R prime is what? Differentiate lah. So R prime of t, differentiate with respect to t. So therefore become, hold on, this one make it more clear. So therefore differentiate x respect to t. Then differentiate y respect to t. Okay, so indeed, your r prime vector is actually your velocity vector. Okay, so this one just d dt lah. Basically, straightforward stuff. So d dt. Okay, so therefore you can see that your r prime is x prime of t, y prime of t. And now you are integrating respect to t. Okay, because after you perform this dot product, you'll get all the functions of t already. Okay, so you can see f1 is a composite function of t, x prime t is also function of t, then plus f2 times y prime. Okay, so everything is function of t. Then you can just integrate respect to t, so it become like single variable integration. Okay, so I'm going to do a demonstration later on. Okay, but in 3D, right, it's the same thing, just that you have F3 component. Because in path in 3D space, just like I mentioned, some path in 3D space, right, you can also take the work done, or you can also compute the line integral. Okay, so therefore you got F1, F2, F3, then you just dot product with the three-dimensional displacement vector. And the three-dimensional displacement vector, if you differentiate, you get x prime, y prime, z prime. Okay, that's the velocity in 3D. Okay, velocity in 3D, yeah? Yeah. So, so therefore work done, I've explained that already. Okay. Okay, so this one maybe okay, so later I'll come back, right? I'll come back. Okay, but for now, I want to demonstrate the use of just now what we have established to get the work done for this particular force field. Okay, so vector line integral over this path C. You see this path C, yeah? So this path C is actually a semicircular path. And because the arrow, right, I draw like that, okay, so that means the start point must be here. Okay, so this one is the start. Then this one will be the end point. Okay, yeah, so what's the first step? So then systematic, must be very systematic. Okay, so what's the first step to do? First step to do is to get your R of t. Okay, always the same, always the same thing, right? So maybe we write it down, write this down systematically. Step one, right? Write R of t. Okay, for given path. Okay, so write the R of t for given path. Now look at this path, it's a unit circle, what? Correct or not? Unit circle, ma. So therefore, what's the thing about the unit circle? The unit circle must be, right, this upper half of circle must be y equals to square root 1 minus x squared. 1 minus x squared. Can okay? So obviously, this path, you can parameterize using this expression, okay? But obviously, it's a part of a circle, right? So part of a circle, I think you use polar coordinates will be better, okay? But nevertheless, let me show you the in Cartesian, right? What you can have, okay? Then maybe I show you the corresponding parameterization, right? For using polar coords. Okay, we have two versions just to have more examples. So now, this R of t, okay, so R of t always for two-dimensional plane must be x of t, y of t. Okay, so therefore, if you let your x be t, then what must your y be? Your y must be root 1 minus t squared. This one no choice. Okay, so basically it has to be like that because your y has to point to the path. Your y has to be pointing to the path. That means must be the y values given by that curve C. So therefore, at any point on the path, right? So this is your R of t. Okay, so x is t, then y must be root of 1 minus t squared, because your x is t, what? Can okay, so you are tracing the path, your R will be tracing the path. No problem, okay? Yeah. So now if you look at this, okay, this one, you get R prime, right? You want to do R prime, then you get a very nasty expression. Okay. Then not only you get nasty expression, later on you still need to dot product with this f. So therefore you can imagine the whole integral become not very nice to evaluate. Okay. So therefore at this juncture, right, maybe you want to consider using polar coordinates. Okay. So let me write down. So this one is perfectly legit. This one perfectly legit. Okay. But this one is Cartesian. Right? This one is Cartesian. Okay, then we say, but since half C, right? Half C is part of a circle. Part of a circle. Maybe it is easier to use polar coordinates. Okay? So what's the polar coordinate version of R of t? Okay? So the polar coordinate version, right, must be x equals to r cos theta, y equals to r sin theta, correct or not? But for path C, you notice that the radius is always 1, right? The radius is always 1. This is r equals to 1. Okay? Or let me put r equals to 1, a small r equals to 1. So which means you always have what? X, it will be r, which is 1, then times cosine. So in this juncture, right, at this juncture, you can actually parameterize with respect to theta, right? If you treat the theta as the polar coordinate, right, whereby you take reference from the positive x-axis. So therefore, do you want to use t? Yes, you can use t. So t can be the angle, no problem. Okay, so maybe we stick to t lah. So in this respect, our t becomes the angle. You can change to theta, no problem. If you prefer theta, I can change to theta, no problem. Okay, but maybe we stick to t. So therefore now polar coordinates will mean that, right, this t becomes the angle. So let's call this angle t. Okay, so you can see r is a function of the angle t. At different angle t, the r is going to point to different points along the curve. Okay, beautiful. So therefore, this can be r cosine t. Okay, so which is 1 cosine t, and the other guy, which is the y component, must be 1 sine t. How about that? So you can see this is so easy. Okay, this is so easy because you have a very easy way, you have a very easy time performing the differentiation. Okay, so this one, angle from x-axis. Okay, so t now becomes the angle from the x-axis as shown here. So now, right, after you get the r of t, because you want r prime, so you just differentiate. So now becomes what? Minus sine t, then cosine t. Okay, so that's it. You got your r prime already because remember your integral, you need f and r prime dt. Okay, f and r prime. So therefore, you have found the r prime already. Okay, can I have the better one? So that's step 1. So step 2. Step 2, write down f or whatever vector field of r of t. Okay, so this is easy peasy because look at your f here. F is a function of xy. So what does this mean? F of the vector r of t means, right, you want to evaluate the vector f at all the xy points along this vector r. So really, this means, right, f of x, but x is x of t, y is y of t. Simple as that. Okay, because you must look at this part. Look at this part. You see? R of t is x of t, y of t, correct now. So if you sub in that particular r of t, right? If you sub in that particular r of t, okay, so since our r of t is using this guy, then your x of t, y of t is really just cosine t and sine t respectively. So you look at this part. Can okay, so this x of t, y of t, is this cosine t and sine t ma? So therefore you just sub in So therefore this guy is really, so this is minus y, correct not? So minus y, but this is y ma. So therefore you have minus sine t. Okay, so let me put the sine t in black so that you know actually this is your minus y. Okay, okay, wait, I want to put one more step so that you can see it. Okay, this vector minus y of t, then x of t. So in a nutshell, right, just sub in the parameterization r of t that you just make. Okay, so this will be your x of t, this will be your minus y of t. Okay, can from this given vector field. So therefore you have minus sine t and x of t will be just cosine t. Okay, so at this juncture you have to be very careful. This one is you sub in the x of t, y of t. You don't sub in the x prime t, y prime t. Don't sub in the velocity. Okay, be very careful because this is a very common mistake because r and r prime looks about the same. Okay, so let me put a note here, right? Let me put a note here. Do not use x prime t and y prime t. Because I see this mistake like many times. Okay, because sometimes you in a rush, right? Sometimes I also make the same mistake. Okay, so do not use x prime t, y prime t, right? Because this is to be parameterized using x of t, y of t. You can see this is not f of x prime, y prime, right? This is f of xy. Xy is at the displacement vector. I mean, sorry, it's at the so-called vector function r of t. Okay, so done. Step 2, so easy. Okay, just sub in, can already. Then last step. So last step is to do the integration. Step 3, do line integral. Okay, so therefore integrate over curve C. Okay, so let me write the what do you call that? The general form first. Okay, then I have to, okay, let me write down the F and R prime first. Then we got to evaluate the limits. Okay, so the limits also important. So R prime is this guy. Okay, wait, I think I better use a different color. Okay, so R prime. So this is my R prime in red color. Okay, then dt. Integrate this dot product with respect to dt, with respect to t. Okay, then we have to ask the logical question. You want to integrate from t equals to what to t equals to what, right? Correct not? But because your t is the angle, this t is the angle, correct not? So that means at the start, t must be 0 at start point. Because it's start point, t equals to 0. Okay, then what about at the end point? T equals to pi Since t is the angle. Understand? Okay, so therefore, this is t equals to 0 to t equals to pi. So this is the setup of the line integral. If you write this down, you get a lot of marks already. Is that right? Okay. Yeah, so the integration is actually quite trivial. So this one integrate 0 to pi. You can see minus sine t times minus sine t is sine square t. Then plus cosine square t dt. But this is obviously integrate 0 to pi 1 dt. Then integrate 1 is just t. Then evaluate from 0 to pi. So therefore it's pi. Okay, so the line integral here is just pi. Okay, so if your force, if let's say F is a force field, right, in newtons, and this path, right, path C is measured in meters. For example, X and Y are in meters. Then this will be pi joules, okay? That means the work done will be in joules, right? Newtons times meters, so therefore joules. Okay, is that right? So 3-step approach. right? Recap. Step one, parameterize the path, write down the vector function, r of t. Then after that, differentiate to get the velocity. Okay, just differentiate each component with respect to the parameter. Step two, write down the f of r of t. Okay, that means whatever you have chosen to parameterize the path here, you have to sub into the vector function, the vector field. Okay, then after that, just take dot product and perform the line integral. Then that's it. Okay. So, well, in many cases, actually some students they just do it in one step lah. Okay, they straight away write this. Can also lah. If you know what you're doing, right, you no need to write 3 steps. Okay, 3 steps, of course, is for clearer presentation. Okay, but if you know what to do, right, like one step, you can just do the integral already. Okay. Yeah, so that will be for this line integral, and then I will also do another exercise, which is for this path that is in 3 dimensions. Okay, that means in 3D space. So you can see the vector here, right? It's a radial vector field. Okay, x, y, z, because it's radial vector field, right? As we have discussed just now. Can Okay, so what is this path? Actually, this path, okay, so the x goes with t, so you can let x be t. So they parameterize the path for you already. Okay, then the y is 3t squared. Then the z, right, is actually 2t cubed. Okay, maybe I can try to draw this. Okay, because it can, no need to draw, but I just want to like visualize the path for you. Okay, so x is t ma. So therefore, this means y is 3x squared. Then this means that z is 2x cubed. 2x cubed, yeah. You see? Okay, because x is t, right? So actually, if you draw out, maybe the path looks like, so therefore this is x, y, and z. So you see y equals to 3x squared. If you try to draw on the xy plane here, right, it looks like that, ma. Correct not? Just look like that. Okay, so maybe let me see, 1, 3, 2. Okay. So start from origin, 0, 0, 0. Stay as a start point. Okay, then the end point is at y equals to 3. So end point is somewhere here. Okay. So that means x must be 1 at the end point. You see, okay, so this is just looking at the y component. But then what about the z component? Z component also is a curve. Okay, maybe put this. So is z as a function of x, right? So therefore, the fella, I think, look like maybe like that. Maybe like that. Let's try my best to draw here. Okay, that's not bad. So maybe the fella look like that. Okay, so when x equals to 1, z equals to 2. So it is 2. Can okay. So of course, this is the what? This is the projection of the curve in 3D onto the xy plane and onto the zx plane respectively. Okay, so how does the 3D curve looks like? Of course, I'm not able to draw this like very nicely, but let me try my best. Okay, maybe the curve looks like that. Or maybe looks like that. Okay, so you got to see the projection. So this start point, then the curve look like that. Yeah, something like that. Okay, doesn't matter. Okay. So if you project down onto the XY plane, you will see the pink one. Then you will project onto the ZX plane, and then you will see the blue one. Okay. So therefore, this is the start, this is the end point. Okay, so the curve maybe go like that. Yeah. Okay, so what is this coordinate? The coordinate would be 1, 3, 2. 1, comma 3, comma 2. Okay, given so this one is end point. End point. Okay, then this one is start point. Start point is 0, 0, 0. Can see from here. Okay, so therefore, this is the start point. So 0, 0, 0. All right. Okay, so you see this like a curve in 3D lah. Try to visualize. Okay, no need to draw. Actually, no need to draw. Okay, we just do the operation. But it's a nice thing to maybe understand it. Okay, so now you see this one like easy. Why? Because they already give you R of t already, what? So you don't need to parameterize yourself. Okay, so you use the parameterization given by them. So therefore, you just get the r prime t. So I don't do the step 1, step 2, step 3 lah. Okay, so you just get the r prime t. So r prime t is 1, 6t, and 6t squared. Correct, oh? Okay, just differentiate with respect to t. Okay, so therefore that's your r prime t. Then you can also write down your f. So f of r of t. Okay, so this guy will be what? So x is t ma. So therefore this will be just t. This x is t. Then y is 3t squared. So 3t squared. 3t squared. Then z is 2t cubed. So it just happens that, right, your f after parameterization by t, it is looking like r of t. Okay, because r of t is exactly x, y, z, what? Can, okay? So therefore, from here, you can see all your functions of t all out already. So therefore, the work done, okay, because you have a radial force field in newtons, so this guy is in newtons, then r of t is in meters. Okay, so therefore, the work done can calculate. Work done is integrate. Integrate, right? You can straight away write down the start and end point. So the start point is 0. Okay, but what's t? T is x. T is x. And you are going from t equals to x at 0. Because x at 0, you see? T is x, to x equals to 1. So therefore, this must be t equals to 0 to t equals to 1. Okay? Because t is actually the x coordinate. So you must follow the x coordinate. Is that right? Okay? So therefore now, you plug in. So plug in, you get this. Okay, maybe let me just write the thing first. So this will be f r of t dot r prime t dt. Okay, so therefore we have integral 0 to 1, and then you just plug in this thing. So take dot product, okay? So then this guy is easy peasy, just a polynomial function. So it's t plus 18, right? 18t cubed, then plus 12t to the power of 5 dt. Okay, so t squared over 2 plus, so 18 divided by 4. So 18 divided by 4 is what? Divide by 4, cannot divide by 4. So therefore, 18 divided by, okay, I put 18 divided by 4 first. T to the power of 4. Then this is 12 over 6, so it's actually 2. Maybe I put 12 over 6 first. T to the power of 5. Okay, so this whole bunch, evaluate from t equals to 1. T equals to 0 to 1. Is that right? So 0 you subtract is all 0 lah. So obviously you subtract in 1, right? You are going to get half plus 18 over 4, which happens to be 9 over 2. Then plus this is a 2 lor. Okay, then minus 0. No need lah. Okay, I just put minus 0. So by right, you should get 7. Okay, which is legit lah, because half plus 9 over 2 is 5 ma. Correct not? It's 10 over 2 lah. So therefore plus 2 is 7 lor. So therefore this will be 7 joules. Because Newton times meters. Is that alright? So you can see the vector line integral actually not that bad, right? The moment you have your r of t can be given, you might have to do it yourself. Okay, then the rest just mechanical lah. Differentiate, then sub in the r of t into your vector field, then after take dot product, then after just integrate. Okay, limits will be determined by your parameterization, like let's say your x is t, and also by the start and end points. Okay, start point to end point. Any questions? So this will be the gist of our line integral. Let me look at the t to the power of 6. T to the power of 6. What is it, t to the power of 6? Oh, yeah, you're right. Sorry, this should be t to the power of 6. I should integrate, correct now? Okay, it is t to the power of 6. Absolutely right. Okay, but the answer is still the same. Thanks. Any other questions? Yep. Okay, can Right, so this will be for the line integral examples. And then now maybe I go back to this slide. Okay. So actually, if you look at your dr, right? Actually, your dr is dx, dy, dz leh. Okay, that means a path in 3 dimensions. Okay, in 3 dimensions, the dr vector, right, actually is given by dx, dy, dz. Why is that so? Because just now we established dr, the displacement vector, is velocity times time taken, dt. So therefore, if you look at what is your r prime. R prime is just x prime, y prime, z prime in 3 dimensions. Then you multiply by dt, which is a scalar. So that means you can multiply the scalar into each vector component. Okay? So therefore, what's x prime dt? Dx what? Correct or not? X prime dt is just dx. Y prime dt is dy. Z prime dt is dz. So therefore, if you want, you can also write this, dx, dy, dz, right, into the dr vector. Okay, into the dr vector. So therefore, your f1, f2, f3, right, can be written in terms of x, y, z. You can see here. Okay, so if you integrate f1 respect to x plus integrate f2 respect to y plus integrate f3 respect to z, sum up, you also get the same answer. Okay, but what is the disadvantage of using this? You probably see immediately, right? Because you need to integrate each component of the vector field with respect to the different variables. You see that, right? So that means you cannot like perform one integral with respect to t only. You have to perform each component. Okay, you have to you effectively, right? You have to perform 3 integrals. Right? Integrate f1 respect to x, then from x start to xn, plus integrate f2 respect to y, from y start to yn, and then do it again for the z direction. So therefore, not efficient. Okay, just not efficient. Can see, right? Instead of performing one integral, you go and perform 3 integral. For example, in the vector field, line integral in 3D. Okay, so therefore, it's better, personally, and also from my experience, to use the r prime t dt variant. Okay, that one will be more efficient. Okay, and somehow you can like simplify because sometimes, like for example, right, this thing can see the x component and y component, you take dot product become simplified expression. Can okay, so therefore this is usually what we do right, using parameterization before we do the line integral. Okay, so now let's take a look at what we mean by a conservative vector field. Actually, it's something that you probably have heard before. And that is, for a vector field that is conservative, that means the so-called work done or the line integral, work done and line integral, they are the same thing, right? So the work done or line integral, right, only depends on the start and end points. They don't depend on what path, right, you take. Okay, so that's why it's called conservative. Why conservative leh? Because whatever path you take, right, doesn't affect the energy consumption. Okay, so if, for example, you look at this diagram here, right? If I move this object from a lower height to a higher height, I need to input energy, correct or not? Because I'm going against the gravitational field. Okay, I move like some object, right, from higher to lower height. So from lower to higher height. So I need to input energy. Okay, but if let's say this field is conservative, then I can say that regardless of what path I take, because there is no friction, there is no energy so-called dissipation medium, right? When I go through any of the path, so therefore the energy consumption is always the same if the start and end points are always the same. Okay, so only when you have friction. Friction means what? Friction means you are taking away energy as you move, right? Because you need to overcome the frictional resistance, for example. Okay, like air resistance, for example. So therefore, if you have friction or any kind of energy dissipation mechanism, right, then your field is not conservative. Okay, so you can see like conservative has to do something with like conservation of energy. Okay, conservation of energy, right, in a certain perspective. Okay, so if energy is conserved, then actually you don't lose energy along the way, due to the friction. You see, so therefore, we have this conservative concept here. Okay, yeah, so if you look at like this example, is trying to show you the gravitational force field. So gravitational force field, X and Y component zero because only got the downward Z component. Okay, because gravity is always pointing down, right? Then therefore the force field depends on your M, lah. Okay, so if the particle or object has mass M, right, then obviously the force will be minus mg. Okay, so you can look at this integral, the line integral. So the line integral is actually giving you the force, is giving you the work done. You see how work done, okay? So therefore, if you perform this integral and then you do the necessary, right, whereby you have minus mg, so what is your, why is there a z prime here? Okay, you have a z prime here because, right, your dr here, wait, let me see. Wait, how come you have a z prime here? So f of x, y, z dot dr. Correct. Because this dr is actually is actually r prime dt, Okay, maybe I should have expanded this. So this guy is dr, the vector, displacement vector, is equivalent to r prime dt. Then r prime must be x prime of t, y prime of t, z prime of t. Okay? So therefore you see the z prime, because the first two components zero for the force field. Okay, then you have a dt here. So you see 0 dot x prime disappear. 0 times y prime disappear because you take dot product. Okay, then you're only left with minus mg times z prime. So therefore you have a minus mg z prime as the resultant. Okay, the resultant after the dot product. So you can see down here, this minus mg is a constant one, so can factorize out. So effectively, you are just integrating dz, 1 dz. So become z, then sub in z1 and sub in z0. So you get, for example, z1 minus z0, but there's a minus here. Okay, so therefore you can swap the terms and become z0 minus z1. Okay, so basically, this is trying to tell you, right, actually, I don't care about what path you take. I don't care what path C you take. It is only dependent on the height at Z0 and Z1. Okay, meaning to say it is only dependent on the height of the start and end points. Okay, so therefore this is a characteristic of the conservative vector field, whereby the line integral is independent of the path taken. I don't care what is the path, C1, C2, C3, or whatever path, right? Doesn't matter. You can curl like, all over the universe, right? Then come back to the same end point and start point, right? Is going to be the same line integral. Okay, so path independent. So therefore, so for a conservative vector field, okay, let's talk about the scalar potential. Okay, because the vector field, when it's conservative, it is also called the gradient field. So just now in the earlier lesson, right, we have talked about that. Okay, so what is the scalar potential of the gravitational field? Now, the scalar potential is going to be just minus mgz plus c. Why is that so? Because you look at your vector field is 0, 0 minus mg. So let me write here. So the gravitational vector field is 0, 0 minus mg. Okay, so that means if you, of course, you can do the same process, right? Integrate, differentiate, compare, integrate, differentiate, compare. Okay, to get the scalar potential, right? You can like go through the long procedure okay, in the morning class, demonstrated in the morning class. But right, if you just do inspection, you can tell that, right, actually this is the scalar potential function. Okay, why is that so? Because if you have minus mgz plus c, then you notice that if you differentiate respect to z, then obviously you get minus mg, what? So this is E sub z, right or not? E sub z must be giving you minus mg. differentiate mgz with respect to z. Okay, or differentiate minus mgz with respect to z. Can so therefore you get this minus mg. Then because you have only a function of z, so therefore if you have p sub y, that means differentiate this function respect to y and with respect to x, you are going to get 0 because this is not a function of x and y. What? Legit, okay? So therefore, this one just by inspection, right? We should agree with the scalar field if you go through the long-winded process. Okay, the integrate, differentiate, compare the thing. Yeah. So you see, now this is the scalar potential. Actually, what is this scalar potential? The scalar potential is actually the potential energy. It's a term for the potential energy because the potential energy is actually mgh, correct? Okay, so there's a minus here because of the convention here, right? So we'll not discuss too much about this, right? Because of convention in physics and mathematics is slightly different. Okay, but never mind about that. What is important is that, right? You notice that just now our line integral is mg z naught minus z1, which is mg z naught minus z1. Okay, then if you expand out, right, is minus mg z1 minus mg z1 minus minus mg z naught. Okay, so which means you notice that actually this minus mg z1, right, is e of x1 y1 z1. That means you sub in z1 into z. Of course, the x1 and y1, right? No need to sub in, because this expression has no x and y. Okay? But you might notice that, right, actually, this scalar potential, you just take the end point. Take the scalar potential at the end point minus the scalar potential at the start point. You are going to get the same result as the line integral. Also that? Can Okay, because, and this makes sense. Why is that so? Because when you do a line integral, you're doing integration, correct? You're doing integration, okay? And then when you are getting the scalar potential from the vector function or from the vector field, you are also doing integration, what? Isn't that correct? So therefore, we can actually use the scalar potential if it exists, if there's a scalar potential, to find out what is the line integral without performing integration. Okay? Without performing integration. That means, let's say you have, let's say the one part of the question asks you to evaluate the scalar potential. Okay, I give you a vector field, I ask you to evaluate the scalar potential. Then you go through the long-winded process. Okay, integrate, differentiate, compare, integrate, differentiate, compare. Then you get your scalar potential function already. Okay, then after that I tell you, find me the line integral, right, from some point to some point. Then actually you shouldn't do the integration again because you already done it here already, what? So what for you going to do double work? Okay, so therefore just make use of the scalar potential, sub in the end point, sub in the start point, take the difference, right? You have the same result already. Okay, so therefore this is just end point at end point, so at end point minus that at start point. Is that okay? Can Okay, so therefore this is what I just mentioned. Scalar potential can be used to evaluate the line integral, right, for a conservative vector field. Only for conservative vector field you can. Okay, so actually this is the proof right, using chain rule and fundamental theorem of calculus. Okay, so due to time constraint, I will not go through. You can go through this pretty easily. So therefore now we have to ask the question, when is it that a vector field is conservative? When is it that a vector field is conservative? Okay, now a conservative vector field that means all conservative vector fields, right? They are gradient fields. They are gradient fields. Okay, why is that so? Because you notice or not? In order for the scalar potential to exist, right? That means the vector field here, this vector field here, must be a gradient vector. What? If it's not a gradient vector, how can you integrate to get the function, to get the scalar function? Because how do you get this gradient vector in the first place? you differentiated a scalar function ma? Agree, yeah? So that means from the scalar function, you differentiate to get the vector field, which is a gradient field. Okay, it's a gradient vector. Then, in order to get the scalar function, the scalar potential function, you integrated the vector field. You integrated the gradient field. So you see this relationship, right? So therefore, the existence of a scalar field, of a scalar potential, depends on whether that vector field, is it a gradient vector or not? It must be a gradient vector. It must be a gradient field. Or else, right, you cannot possibly integrate to get the scalar potential. Understand? Okay? So therefore, if it goes one way, right, it must go back the reverse way lah. This is what I'm trying to say. Okay? So therefore, all conservative vector fields are gradient fields and all gradient fields are conservative. Okay? Otherwise, right, there cannot be this relationship between a scalar potential and a gradient vector or a gradient field. Okay? So, but then how can we check easily, right, without doing the nasty integration, differentiation and comparison loop? Okay, how is there a way to check not that, hey, this vector field, right, whether it is a gradient field or not? Actually, the answer is yes. Okay, the answer is yes. Because, right, you just take the curl of the vector. If the curl of the vector field is a zero vector, you get zero, like what we did just now for our curl examples. If you have a curl being zero, right, then it must be a gradient vector. It must be a vector field. It must be a gradient field. Okay, what's the reason? The reason is here, ma. Can you see not? So, isn't this a gradient field? Because you take the gradient of a function, ma. So this is a gradient vector. Okay, gradient vector or gradient field lah, because you take the gradient vector. Okay, so look at this. What is this? This is E sub x, E sub y, E sub z ma. Let's say in 3D lah. Okay, E sub x, E sub y, E sub z. Then this is the curl, right? Correct or not? You take the gradient operator cross the vector field. So you're taking the curl. Okay, so therefore, look at this. Look at this operation. So to get the first row, you differentiate E sub z with respect to y. Okay, so Ez sub y, differentiate E sub z with respect to y, minus differentiate E sub y with respect to z. Then this must give you E sub yz ma. Understand? Okay, so if you understand the first row, then of course you just extend to the two rows. So what happens is that, right, we notice that it is always E sub, for example, the first row, right, E sub zy minus E sub yz. Second row, you get E sub zx minus E sub xz. Then we get E sub yx minus E sub xy. So therefore, you notice or not? They are mixed partials and they are the same. Because differentiate respect to z, then differentiate respect to y is the same result if you were to differentiate respect to y first and then differentiate respect to z. Okay? So therefore, I mean in the earlier what do you call that? Topic, right? We mentioned right now, we noticed that f sub xy is always equivalent to f sub yx. Okay? So therefore, symmetry of mixed partials. So this is the symmetry of mixed partial. They are always the same. So since they are always the same, then you will just minus off exactly. So you get a zero vector. Can Okay, so you notice that in this statement, right, I didn't say what is E. This is generic description, okay, for a scalar potential function. I didn't even put in any function. Okay, but it always turns out to be like that. So which means it applies for all scalar potential functions or scalar functions. Okay, so simply, we just check if the curl is zero. If the curl is zero, then you can use the scalar potential to evaluate the line integral. Okay, if the curl is not zero, sorry, no such scalar potential. You can try your integration, you integrate different things or different rows, right? You're going to get different answers. So that means there is no unique scalar potential. Okay, that means there is no one scalar potential for some vector functions. Okay, so now let's take a look at this example. So from the last exercise, is the force field F conservative? If so, evaluate the line integral, blah, 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 over any path and reconcile the value obtained earlier. Okay, so this one last example. I can tell you, you look at this x, y, z, you know it's radial, right? The vectors, the force vectors are just pointing outwards only from the origin. So therefore, this guy is going to be conservative. Okay, but of course, that's just by argument, right? We can always check, ma. So therefore, we just check. So check the curve. Check curve. So therefore, take the cross product. Okay, so if you take the cross product, this is del x, del y, del z, cross x, y, z. Okay, so therefore we have first row, z sub y. That means meaning to say, differentiate z respect to y, minus differentiate y respect to z. Okay, so obviously it's going to be 0, right? So 0, 0, 0. So indeed, this is a 0 vector. Okay, so therefore, F is conservative. Okay, so once F is conservative, it means that F is a gradient field already. It's a gradient vector. Okay, so therefore, now we are supposed to evaluate the line integral over any path. So what does that mean? That means we need the scalar potential. Okay, so since F is conservative, right? That means there is a scalar potential. So therefore, scalar potential, that means the function that you differentiate to get this vector f, to get the gradient vector f, exists. So let's call it E of x, y, z exists. Okay, so once you have conservative vector fields, so now how to get the E of x, y, z? Go through the earlier, what do you call it? Earlier process. Okay, so recap. So now you have your f sub x here, right? This is your f sub x, or rather in this case, E sub x. Okay, so E of x, y, z is going to be integrate E sub x with respect to x. Okay, but your E sub x is this first component, because now you differentiate respect to x, right? You get the first guy. Okay, E sub x. So therefore, now you have integral x dx. So integration of x dx is going to be x squared over 2. Okay, but remember, you don't just put x squared over 2 because you integrate with respect to x, right? And your function can be a function of y and z as well. So therefore, you must put in a g of y and z, some function of y and z. Okay, because you differentiate this g of y and z, right, respect to x, you get 0, right? Okay, so therefore, you need to insert this function. Okay, so then to find this g, right, then what you do is that you differentiate. So therefore, E sub y. So E sub y is going to be, differentiate this. So you're going to get G sub y, okay, of y and z. So now you compare. Compare with E sub y. So this is E sub y. So E sub y equals to y. Okay, so then you're going to get G sub yz must be equivalent to y. Is that okay? Can right? Because you got E sub y, you only have G sub y Then this is E sub y equals to y. Then no choice, that means G sub y must be y. Can So therefore, if G sub y is y, then what is G? G of yz must be y squared over 2. Integrate y So integrate y dy. So therefore, okay, sorry. Integrate G sub y dy. Okay, so you get y squared over 2. But you have a function of z also. So therefore, plus h of z. Okay, so basically what we did earlier. Then after that, right, what is your E of x, y, z? So E of x, y, z, now you're getting x squared over 2 plus y squared over 2, then plus h of z. Okay? So I think you know where we are going. Hold on, let me just add the next And next page. Okay, so from here, right, you get E sub Z. So E sub Z is going to be just H prime Z. Okay, then you compare. Compare with E sub Z equals to Z, because this is your E sub Z. Okay, so you are going to get H prime Z equals to Z. So what's H of Z? Z squared over 2 plus C. Okay, so it all makes sense, right? And then your E of XYZ is just x squared over 2 plus y squared over 2 plus z squared over 2 plus c. Is that right? Okay, so we found the scalar potential function. And if you were to differentiate, you differentiate respect to x, you just get x. Correct or not? 2x over 2, so you just get x. Correct? Then the y and z are like constants when you differentiate respect to x. Okay? So I think quite easy to see. So now, after we got the scalar potential, then now we evaluate the line integral. Okay? From 0, 0, 0 to 1, 3, 2. Right? Same as the earlier example. So therefore now, line integral, okay, over some path C, f dot dr is just E of the endpoint 1, 3, 2. 1, 3, 2 minus the E scalar potential at the start point 0, 0, 0. And so therefore you notice that this is what? This is 1 square over 2 plus 3 square over 2 plus 2 square over 2 plus C. Okay, the C will cancel off in the end, right? Then you have this part, right, which is just 0, 0, 0. So 0 plus 0 plus 0 plus C. Okay? So therefore you can see that this is going to give you the same answer. So this guy is going to give you half plus 9 over 2 plus 2, and this is equivalent to 7. 7 joules. Okay? So which is the same as earlier. Okay, and this is to be expected. Right? This is to be expected because we just showed the result from the earlier slides. Okay, so you can use the scalar potential, if there is one, to compute the line integral over any path. Because it is now path independent already, if your vector field is conservative. Okay, or it means that it is a gradient vector or gradient field, right? Then actually, you just give me the start point and end point, right? I don't care what path you take. It's going to always give me the same line integral value or the work done value. Questions on this concept? Okay, good. Yeah, so definitely need to practice. Okay, so now this will be the very, very last part of this topic and we're almost done. So maybe just bear with me for a bit more. Okay, so this thing is called Green's theorem. And this is a very interesting and very beautiful result, if you ask me. Okay. Now you see, okay, so I state the thing first, then I tell you the concept behind. It's actually very, how to say, very natural, if you ask me. Very logical, okay, that you're going to get something like that. So the Green's theorem actually relates the curl of a vector field, let's say f of xy. So of course, we say that the curl always, by right, have to have 3 dimensions. That means the vector field by right must be in so-called 3D Okay, but in this case, we can always say that the z component is 0. Okay, so the vector field f, right, is, I understand, is f of xy, but the curl, you can just treat the z component being 0. Okay, because the field is only in the plane, so there's no z component, right? So the z component will be 0, Okay, because the curl, we always need like 3 components, okay, to compute the curl. Okay, that's not important. The important thing is that, right, it relates the curl of a vector field inside a closed curve. Okay, the curve must be closed. The curve cannot be like open like that one. right? It must be closed. Okay, to the line integral that is along the curve. Let's say you look at this blue closed curve, right? If you perform the line integral, you are going to get this right-hand side, correct not? So therefore, the funky looking circle here represents closed. So this circle, this circle means C is a closed loop. Okay, so only if C is the path is a closed loop, right? Then you can write this circle. Okay, but if you don't write, it's also okay lah. Doesn't matter, right? It's more how to say specific here. All right. Now you see, so the concept is like that lah. The concept is right. If you go and integrate over the domain D, that means integrate over this region D. So double integral. Okay, double integral. Right. So double integral over the region D of what? Of the curl of the vector field. So the curl of the vector field, because your vector field is in 2 dimensions. So let me draw. This one I mentioned just now. Okay. So this is your X, this is your Y. So you can see that this vector field F, right, is only in the plane, This vector field F is only on the plane because it's F of xy, what? Can you see, so therefore, let me draw maybe the vector field like that. Okay, so I draw a few vectors, So this is my vector field F, which is on the plane. Okay, but then if you take the curl, how you take? So this curl is cross. So because this is only f of xy, so what we do is that you still have your differentiate with respect to x, differentiate with respect to y, differentiate with respect to z. Then you cross. So this f becomes f1 of xy. Okay, f2 of xy. But you don't have a third component. So the third component is always 0. So therefore, you can see that this part, right, is on the xy plane. Okay, because no z component, what? So that means the arrows here, right, is always flat on the xy plane. It doesn't like stick out, no? Cannot stick out, right? Once it stick out, then got z component already. Understand, right? Okay, so therefore this vector field F only got 2 components only. Then you look at this cross product. If you look at this cross product, you notice that you are going to get this result. So therefore, this is going to be what? Del X operate on F2. Okay, so this becomes del F2 del X minus del F1 del Y. So this is the code. Is that all right? Okay, and this actually is only, I just wrote this is in the Z component. Okay, hold on. Okay, let me move this to this. Okay, so when you compute this curl, right, you notice that if you cover this first row, you take this one, operate on 0. So you get 0, correct? Then minus del z on F2. But F2 is only a function of x and y, what? So therefore it has to be a 0. So 0 minus 0. Okay, for the x component. Then for the y component, you also will get 0 minus 0. You can check. Then it's only for the z component, you have this result. So therefore, this z component will be del f2 del x minus del f1 del y. Okay, so this is exactly this. You see, because you dot k, why is it that you dot k? The reason is because, right, you want to have the curl that is the curl so-called the curl magnitude. You can say that it's like something like a magnitude of the curl. Okay, so you want like to know how much the magnitude of the rotational effect is without considering the direction. Okay, and because the direction, there's only one direction, the direction is in the Z direction, that is pointing out of the plane. Okay, so therefore you are looking at this here. You see? So this is the component. Okay, the Z component, because there's only Z component, there's no other components for the curve already. Right? Simply because your vector field is on the plane. Okay, it's a two-dimensional vector field, like, if you will. Right? So therefore, coming back to this part, okay, so I've evaluated this expression already. Now, what's important is that, right, if you sum up, because you're integrating, if you sum up all the curves in the region, you are going to get a value that is the same as the line integral along this curve C. Okay, and what's the concept behind here? Now, the concept behind here is this. Now, imagine, right, this is a velocity field. So F is like a velocity field. Now, in this velocity field, let's say you go and stir, okay? So which means imagine you have a coffee cup, lah. Okay, you have a coffee cup. Then what you do, right, is that you go and take a spoon, you stir. So you stir, 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 you stir, stir around. So when you stir, right, when you stir, let's say in the counterclockwise direction, right, then you can imagine if you have, let's say, for example, a biscuit. Okay, maybe you put the biscuit here. Okay, at the edge of the cup lah. Let's say the biscuit is at the edge of the cup. Now, you notice that as you stir the coffee or tea lah, you stir inside, right? Now, you're going to cause this biscuit to move. This biscuit is going to flow, is possibly going to flow along the edges, near the edges of your coffee at the periphery of the cup. Okay, right? But I mean, how come there's this effect? Of course, there's this effect lah, because you stir, right? That means you are trying to make the flow, right, go counterclockwise, you know. Okay, so if you stir around, right, you sum up all the curl because of the stirring, right? You are going to cause there's you're going to cause an object, right, to flow around a path. You see that? Okay, so therefore, right, if you sum up all the circulation or the rotational effect given by the curl in some closed path or in some closed loop, right, you are going to have a net circulative effect on the boundary, which is the effect causing the biscuit to move off. Okay, so and that represents the line integral. Okay, so you can see that this is something very, how to say, something that we can observe in our daily life. Okay, don't believe, right? You can throw a biscuit into your coffee tomorrow, then you just like stir the center. Then you see the biscuit move around. Okay? So this statement is called Green's theorem, lah. Right? It's called Green's theorem. Okay, so the positive direction is always counterclockwise because the Z direction is positive pointing out of the screen. Okay, so you use your right hand, right? You're going to see your counterclockwise rotation. Okay, so that's why it's called Green's theorem. This guy is called Green's theorem. And we are not going to go through the proof, right? There's a proof and you can actually go through it yourself. But we are just going to make use of the Green's theorem in solving this example. Okay, let me see how many examples I have. Okay, I have two more examples, so just bear with me. Possibly I will just exceed until 7 o'clock. Okay, then we go for dinner. So, okay, let's continue from an earlier example. Use the Green's theorem to evaluate the line integral of f over the closed curve C. So it actually turns similar to last example, but in the last example, right, the curve C is not closed. It's only the semicircular part. Okay, but in this case, we close it really, right? Then after that, we calculate the line integral directly to verify that the number is the same as that given by Green's theorem. Can okay? So when we use Green's theorem, right, that means if they ask you to use Green's theorem to evaluate the line integral, that means you cannot evaluate the line integral directly. Okay, so the line integral over some curve C. Now this curve C is closed. It's closed. So f dot dr. F dot dr. Now, don't integrate this directly. You have to integrate the double integral. So over the region D. So this one region D, Then del F2, del F2, del X. minus del F1 del Y. Okay, dA. So over the region, over the area region. Okay, you have to compute this double integral. If not, you are not using Green's theorem. Okay, if you compute this directly, then you never use Green's theorem. What? Okay, so you have to compute the double integral. So now look at this region D, and you need to compute this. But what is del F2 del X and del F1 del Y? Easy, just differentiate accordingly. So double integral. Okay, later on, then we put in the limits. So del F2 del X is, because this is your F1, this is your F2. So del F2 del X is just 1. 1. Okay, minus del F1 del Y is minus 1. So 1 minus minus 1. Any objections? Just differentiate F2, which is X, respect to X, get 1. Differentiate minus Y respect to Y, get minus 1. Okay, and this is minus. So 1 minus minus 1. Can So then this is just integration of 2 dA. Integrate 2 dA over the region D. Okay, but 2 is a constant, right? So therefore it becomes double integral, factorize out the 2, double integral of region D, 1 dA, right? This one. So what's integrate 1 dA over a region D? This guy, we mentioned before, it is just the area of region D. So 2 multiplied by the area, 2 times area of region D. Okay? Because this is this. This one just get the total area of region D. Is it? Okay? So therefore, what's the area? Pi r square over 2. So it's 2 times pi 1 square. Pi 1 square over 2 because it's a semicircle. So therefore, the answer is pi. Is that all right? Yeah, okay. So therefore, I've used the Green's theorem to evaluate the line integral. Okay, then I'm supposed to calculate the line integral directly to verify. Okay, but actually, just now I have calculated the line integral over the semicircular part already. Okay, so I'm going to say that, right, over this semicircular part, I call it C1. So let me just draw some dotted lines to show you. Okay, this one called C1. C1. Then after that, right, got another part, which is the bottom part. So this bottom part. So I call it C2. Okay, so if I integrate this line integral directly, I'm going to break up into 2 parts. I need to break up into 2 parts. So I firstly integrate over C1 first, then the same F dot dr. Okay, then plus integrate over C2, then F dot dr as well. Is that all right? Okay. So this orange part, this one we found already. Right? Found in earlier example. Okay, so this one later we just get the value out. Okay, then this C2, we must put the direction carefully. So the direction is like that. Okay, so let's evaluate the second line integral directly. Right, this integral. Right, so for C2, what is the parameterization? Let's call it R of T lah. Okay, R of T. So R of T, you can see that C2 is just minus 1 to 1 in the X direction. In the X, right? X go from minus 1 to 1. Then what's the Y value? Y value is 0. So therefore, X of T, Y of T. So very clearly, Y has to be 0. Okay, Y has to be 0 because Y means the Y component of C2. C2 is entirely on the X-axis. So no Y value. Y must be 0. X must be what? X can just be T. Okay, so let x be t, but y must be 0. Can So therefore this t, right, will go from where? -1 to 1 because t is x, what? Okay, so this, okay, so later then I write down. So once you have this, right, then actually you can do your r prime t. So r prime t must be 1, 0. Obviously lah, because you have to traverse in the right direction, from the left to right. So positive x, you see? No y, but positive x. So velocity is always going from left to right. Can Okay? Yeah. So therefore now you get your r prime already. So now what about your f? So your f, right, is going to be, so f of r of t. So you just sub in, no? So you can see that your x is t, but your y is 0. So this will be 0t. Can Okay, I use here. So therefore now perform the line integral. So this guy. So this guy is equivalent to integral f of r of t dot r prime t dt. Okay, then t from where? T from, as I mentioned, right, -1 to 1. T equals to -1 to 1. Okay. So this one, let me write here. Since t equals to x. Okay. Yeah, so integrate -1 to 1. Then this one is 0t dot 1, 0. So what do you get? You get 0 leh. Integrate 0 times 1, 0, plus t times 0 is 0. So integrate 0. So this guy is a 0. Okay, because it's a definite integral. Can Okay. Then from earlier example, what is this? You notice that this one is exactly pi. There. You see? The answer here is pi. Okay. So over the semicircular part, right? The line integral is pi. So that's why the end result is pi plus 0 ma. So pi plus 0, which gives pi, which is the same as that given by the Green's theorem. So it has to be so lah. Okay. So therefore, this guy is pi plus 0, which is pi. Okay. So expected. Same as Green's theorem. Is that right? Okay. Can So you can see that actually what's the advantage of using Green's theorem? Can have advantage, right? But can be disadvantages also. Actually, it depends on the curve given, the path given. It also depends on the vector field. Okay? Because sometimes for certain vector fields, right? Let's say if you differentiate, you need to use the product rule, chain rule, all those. Okay, then it's possible that your curve is very messy one. Okay, that means it is getting more complicated as you differentiate. Let's say you need to use quotient rule, for example, then that will be the worst. Okay, so therefore, if let's say your derivatives inside this Green's theorem expression, right, is more complicated, it's very complicated, then this double integral not easy to perform because of the complicated integrand, then Green's theorem will not be beneficial. Okay, it might be more beneficial to integrate the line integral directly. Okay, but of course, you don't have to worry about this because the exam, right, the question will tell you, okay, directly compute the integral or use Green's theorem. Okay, so you don't have much of a choice, right? We tell you, you just follow the instructions. Can Okay, but I'm just telling you practically practically, right? But in this case, you can see that Green's theorem is much easier because this derivative is very simple. Okay, it turns out to be a constant. So therefore, it is very easy to find the line integral using Green's theorem in this example. Okay, and the other comparison is that, right, if let's say your closed loop is composed of many, many different functions, right? Like for example, this one is only two functions. One is a semicircle, the other one is a straight line, right? So if it's only two so-called separate curves that link together to form the closed loop, if it's two, right, then it's okay. Then maybe the line integral is reasonable to compute. But if let's say it's comprised of like many curves pieced together, then obviously you want to do this integration, you have to break it up into many parts. So that might not be efficient really. Can okay? So therefore, in this respect, maybe the Green's theorem will be faster. Okay, last example for this course. Okay, use the Green's theorem to evaluate the line integral below over the closed curve C, which is a triangle with vertices, blah, 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 orientated clockwise. Okay, so now draw. So this is your X, this is your Y. So I say this one is minus 1, 2. So minus 1, 2 is maybe somewhere around here. Okay, so this one is X equals to minus 1, Y equals to 2, this point. Then 4, 2. So 4, 2 is, okay, 4, 2. 4, 2 is somewhere here. So 4, comma 2. Then after that, 4, 5. Oh, Y equals to 5. Okay. So then maybe I bring down the 1, 2, and 4, 2. Then I put the 4, 5 maybe here. And so I got 3 points. So then I draw, right? Draw the triangle. Can? Okay. So therefore, this is our curve C, and it's orientated clockwise. So clockwise must be like that. Must be like that. This is clockwise, Okay, it's go in this direction, right? Yeah, so this is my curve C, my closed loop curve C. Okay, and then they asked me to use Green's theorem to evaluate the line integral below. So this is a line integral, and it's written in the differential form. Okay, so actually, this form is like that lah. This form, this guy, is actually the f dot dr. F dot dr. Okay, so therefore this f dot dr is what? Is f1, f2 So the f1 must be sine x squared. Okay, then this is 3x minus y for f2. Then dot dx dy. Okay, so I just like write this out for you so that we can recognize the f1, f2 more explicitly. All right. Yeah, so since we have to use Green's theorem, that means the integral of f dot dr has to be done from the double integral. Okay, so of course the curve C is closed. That's why we can use Green's theorem. Okay, but now you know what's the story. The story is, right, this one is clockwise. Okay, clockwise. But to use the Green's theorem, actually you have to make sure that the curve is counterclockwise. So therefore, all you need to do is to put a minus. So just put a minus. Okay, because the curve C by right has to be orientated counterclockwise. But this one is clockwise. Okay, so you just add in a minus. Okay, then it becomes clockwise already. Sorry, then it becomes counterclockwise already. Okay, so we can say since C is counterclockwise, or since C is clockwise. Okay, so you just throw a minus. Right? That will make C becomes counterclockwise. Yeah, so now differentiate. So you can see that F2 sub x is 3. Okay, F2 sub x is 3. Then F1 sub y is 0. Then this becomes dA. Okay, wait. I better write first. So del F2, del F2 del x minus del F1 del y. Okay, I better write down more clearly. Right, and this is maybe over region D lah. Okay, so therefore I have a negative double integral over region D. Then this F2 sub x, so F2 sub x is 3 Differentiate 3x minus y with respect to x. So just 3. Okay, then differentiate sine x squared with respect to y. Minus 0. dA. So therefore this is minus 3 double integral of 1 dA for the area of region D. Okay, so this is similar to what we had earlier on. Minus 3 times area of region D. Okay, so the answer is trivial. So triangle ma. So half base times height lah. So that means we are getting half. So what's the base? The base is 4 minus minus 1. 4 minus minus 1. So 4 plus 1. Okay, half base times height. So the height must be what? The height must be 5 minus 2 lor. Okay, so therefore it's minus 3 multiplied by half times 5 times 3. So it's actually 15 over 2. Okay, so the answer is just minus 45 over 2. Any questions? Okay, so of course I gave you like easy examples here, whereby this integral always ends up to be a constant, integration of a constant, so much so that we can just use area formulas to find the area of the region, given that it's a simple region. Okay, but in the tutorial, you will see that, right, it is possible that you must integrate this. That means, if let's say this is a function, and then your limits for the region D could be functions, that means you have to fall back on your topic 7, no? Right? Because topic 7 is performing double integration, triple integration, etc. Right? So then you must make use of the knowledge and concepts covered in topic 7 to perform this integration. Is that okay? Any questions? Let's look at if there are questions. Nope. Anyone? We are done for this topic 8. I hope I didn't go through too fast. Anyone with questions? I hope I'm not the only one left talking to myself.
No.
Yeah, any questions or not? How do you know if it's clockwise or anti-clockwise? Yeah, it has to be stated. That means the path, so answer Ping Jie. Okay, the path has to be stated. That means to say I must describe to you the path as well as how it is orientated. Okay, it's possible that I give you the graph lah, then I draw the arrow lor, right? So you have to see whether it is counterclockwise or clockwise. Okay, or I can also state. So I have to tell you, because if I don't tell you, then it's ambiguous already. Okay, meaning to say it could be clockwise or counterclockwise, and then the answer will differ by a negative lah. So I have to tell you. Okay, so you have to, I mean, as in the question will state. Any other questions? All right.
Prof, just checking,
Yes.
the shapes will all be stated, right? Like the shapes if needed, because like I just noticed they
Oh, it will
say
be stated.
okay.
The path, the shape, the loop, whatever, that one I have to give you. I'll give you like a description. Okay, it could be the graph itself and can also be like tell you it's a triangle or it's a square or it's a circle or what, right? So therefore you either you draw the path, you sketch out, or you can just refer to the graph given directly. So if I give you the graph, then maybe you need to produce the parameterization. Okay, that means the R of t if you are performing the integral directly. Okay, then I could also possibly give you the R of t directly. If I give you R of t directly, then you just mechanical already, like just find R prime, then after that take dot product, then after that integrate. But I have to tell you the information clearly. Is that all right?
Yeah.
Any other questions? So probably you need to review through lah, because the first time you see this thing, right, it's a bit how to say, nasty. Okay, because vector calculus is nasty, right? So I strongly encourage you to review this video by 3 Blue 1 Brown. Actually, this is a very excellent channel that describes many of the difficult concepts in mathematics. Okay, which is covering many of the concepts that you'll be learning in throughout Math 1 to Math 3. Okay, so this 3 Blue 1 Brown, it has very nice animations of the vector fields, what is a divergence, what is curl, what is Jacobian, and all those things. Okay, so it also relates to like magnetic, electric fields, electromagnetic fields, etc. Okay, so yeah, so please review the video to improve your so-called visualization and understanding. Right, so if you have no more questions, then think we call it a day. Then I'll see you tomorrow. Possibly tomorrow I will be only able to go through tutorial 7. Okay, so we finished tutorial 7, right? Make sure you have strong foundations in the multiple integration, right? And then maybe next Monday or Tuesday, I'll discuss with you tomorrow lah. Okay, next Monday or Tuesday, right? We have online lesson or face-to-face, probably online lah, because the recording is much easier, right? So then next Monday or Tuesday, then we go through the last tutorial, tutorial 8. Okay, yeah, so yep, that's all for this extra class. Okay, thank you very much for attending. Goodbye, everyone.
Thank you, Prof.
Thank you. Thank you.
Thanks, bro.